Now try to solve the latest gate questions which has appeared from the Unit 5 and Unit 6. The total time allotted for a question is also represented at the top. Now let's check out the solutions. In the question, the metal work function is provided, and to find the semiconductor work function, we have the energy band diagram, and the semiconductor work function is defined with respect to vacuum energy level and the Fermi level of the semiconductor. We can split the energy from vacuum level to conduction band energy level and conduction band energy level to Fermi energy level of the semiconductor. By simple calculations, we can find the energy difference between intrinsic Fermi energy level and the Fermi energy level of the semiconductor to be zero point 0.3 electron volt. Therefore, we will find the semiconductor work function to be equal to 4.8 electron volt, which will give us metal to semiconductor work function to be equal to minus 0.93 electron volt. We have studied the formula for threshold voltage in the unit 5. In the question itself, it is provided that there is no charge present within the oxide. Therefore, we can cancel the term consisting of trapped oxide charges. And also, if you recall, the Fermi energy level is nothing but the difference between the intrinsic Fermi energy level and extrinsic Fermi energy level in the semiconductor, which we have already calculated to be equal to 0.3 electron volt. This is a modified equation of threshold voltage in which there is no term consisting of trapped oxide charges. All the parameters in this equation are provided or have already been found out except magnitude of depletion charge per unit area, which we are actually supposed to find. After putting all the parameters in this equation and calculating, we will find the depletion charge per unit area to be equal to minus 1.7 into 10 raised to the power minus 8 coulomb per centimeter square. But since we are supposed to find the magnitude, the answer will be 1.7 into 10 raised to the power minus 8. For the second question, in the 6th unit, we have seen body biasing effect where we have find the threshold voltage when there is a biasing between body and source terminals of MOSFET. There we find the threshold voltage to be equal to threshold voltage when there is no biasing plus under root of 2 into magnitude of charge on an electron multiplied by doping concentration into permittivity of the semiconductor, which is silicon, which can also be written as relative permittivity of the silicon multiplied by absolute permittivity of the vacuum divided by capacitance per unit area whole V multiplied by under root of 2 times of Fermi energy level plus magnitude of body to source terminal voltage difference minus under root of 2 times of Fermi potential. Now, if we differentiate the thermal voltage with respect to body to source terminal voltage difference, then we will find this expression. It is also provided in the question that the biasing voltage between body and source terminals are significantly greater than the Fermi potential. Therefore, in the denominator we can neglect the Fermi potential with respect to body biasing voltage. And also, capacitance per unit area can also be defined as permittivity of the oxide divided by thickness of the oxide. Permittivity of the oxide can also be represented as relative permittivity of the oxide multiplied by vacuum permittivity. By substituting the changes, we will find this modified formula. In this equation, all the parameters are provided in the question except the doping concentration Na, which we are actually supposed to find. Putting the values of different parameters in this equation and further calculating, we will get doping concentration to be equal to 7.375 into 10 raised to the power 15 per centimeter cube. For the third question, we already know drain to source current to be equal to mobility of free electrons multiplied by capacitance per unit area divided by 2 into aspect ratio, which is width of the MOSFET divided by the length of the MOSFET multiplied by the square of gate to source voltage minus threshold voltage. Remember that this is the equation of drain to source current when the MOSFET is being operated in saturation region, and it is provided in the question that the transistor is at the edge of saturation. Therefore, we can apply this formula. We are provided that gain to source voltage is 1 volt. Therefore, after putting the value of gain to source voltage and other parameters in the equation of drain to source current, we will get this equation. But here also, we have to keep in mind that the drain to source current which we have found in this equation is actually in milliampere. Now, if we carefully look in the circuit diagram, then we can apply a KVL across driving voltage VDD, drain resistance RD, and drain to source voltage. By KVL, we will find drain to source voltage is equal to drain to source current multiplied by 20 plus drain to source voltage. Here, even though resistance is provided in kilo ohms, we have written only 20 because the drain to source current which we have just found is in milliampere. The other two voltages, drain to source voltage and driving voltage, we will be assuming them to be in volts only. Drain to source voltage is provided. We can put the value of driving voltage and drain to source current in this equation. Also, at the edge of saturation, we know drain to source voltage is equal to gate to source voltage minus threshold voltage. Gate to source voltage is provided to be 1, which will give us drain to source voltage to be equal to 1 minus threshold voltage. Now if we put the value of drain to source voltage in the above equation, we will get this equation. Simplifying it, we will get a quadratic equation. After solving, you will find we have two values of threshold voltage. One is 1.6 volt and the other is 0.5 volt. It is already provided in the question. Gate to source voltage is 1 volt. Then there is no way the threshold voltage is going to be greater than gate to source voltage, because if that becomes the case, there will be no current flowing inside the MOSFET, at least ideally. Therefore, the only possible value for threshold voltage is 0.5 volt. This question is a MOS capacitor which I have taught in Unit 5. However, the shown formula I have taught in Unit 6. Unit 5 and Unit 6 are very much related to each other. In the Unit 6, we have seen the inversion charge density is equal to negative of oxide capacitance per unit area into gate voltage minus threshold voltage. There are two conditions for which we will write two different equations. Now simply subtracting equation 2 from equation 1, we will get this equation. In this equation, we have all the values except inversion charge density in the second case, which we are actually supposed to find. Putting the value of different parameters and further calculating, we will get inversion charge density to be equal to 5.6 microcoulomb per centimeter square. We have studied the formula for flattened voltage to be equal to metal to semiconductor work function minus trapped oxide charges per unit area divided by capacitance per unit area of the oxide. Capacitance per unit area can be found out by calculating permittivity of the oxide divided by thickness of the oxide. Flattened voltage is also provided to be equal to 0 and metal work function is also provided. After calculations, we will get the semiconductor work function to be equal to 4.32 electron volt. We know the drain to source current equation for the MOSFET operating in linear region. All the parameters are provided except gate to source voltage minus threshold voltage, which is also referred as overdrive voltage. After calculation, we will find the overdrive voltage to be equal to 1.05 volts. In the new case, the drain to source voltage is increased to 1.5 volt, which is greater than overdrive voltage. Therefore, when drain to source voltage is increased to 1.5 volt, the MOSFET begins to operate in saturation region. The formula for transconductance of the MOSFET operating in saturation region is equal to transconductance by meter multiplied by aspect ratio into overdrive voltage. We have all the parameters of this equation, and calculating, we will find the transconductance to be equal to 52.5 microampere per volt. If you have solved the questions, then it is good. If you have done any mistakes, then try to solve them again.